Hi, folks. This week we're talking about the life and death of stars. Now, this personally, I think this is one of the coolest topics that we have in introduction to astronomy. Where do these fantastic objects, where do these stars come from? Now, one can think of our galaxy. Our galaxy it's a barred spiral galaxy. We'll study galaxies in a little while. Um, but what we have is we have this huge rotating disk of gas and dust. We have a central core in the center, and then we have the disk, and then we have this called the halo. There may be these little groupings of very old stars that are in little globular clusters that are orbiting around the center of our galaxy. But in general, we're going to be concerned mainly with what's going on in the disk of the galaxy. That's where new star formation occurs. Now, in that disk, we have these rotating shock waves that are traveling around the disk itself. And we know what these shock waves are because we look at other galaxies and we see them. They're all lit up because when this shock wave comes through, it triggers star formation. The shock wave travels through some cloud of dust and gas, molecular hydrogen, molecular helium mostly. But then there's also some soot, some carbon, some oxygen, nitrogen, helium, things that are left over from previous iterations of stars that have lived and died, that have seeded it with all these molecules that we think are essential to life. Okay, and as it passes through this molecular gas cloud, it makes certain portions of this gas cloud more dense than others, and that more dense means more mass. And it's got gravity. It's going to start attracting the things around it. Not much at all. It's just going to start coming in very, very slowly. This could happen. This is going to take millions of years to happen. Okay, and then what happens when you compress gas? It warms up. Not a lot. Out there, it's about 2.4 Kelvin. It's about 2.4 Kelvin, maybe a little bit more, but that's enough temperature to raise the pressure. To raise the pressure a little bit, and it's gonna that little area where it's a little more dense. It's gonna hold itself up until that collapse and that heating and that pressure, that the heat that it causes, can radiate away. Now, space is a very cold place. It's easy to rotate and radiate away, but it's not a huge temperature difference for it to radiate very quickly. But it's going to reach some steady state because as it radiates away some of that thermal energy, that means that the pressure is going to drop, and the gas cloud's going to compress. It's going to heat up again, and it's going to reach this equilibrium. It's going to reach this equilibrium, and it's not going to heat up very quickly, but it's going to start collapsing, 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 and then that rate of collapse is going to increase. It's going to increase, and then very near the last, over a period of just like 500,000 years, it's going to go from this very hot star forming region to little places inside that star forming region where things are going to start to glow. They're going to begin to glow not just in the infrared, but in the UV and in the visible light. And we're going to be able to look out there, and very often we can see these areas that are lit up in blue. Lit up in blue. To the naked eye, they all look blue. If you want all these fantastic images with the different colors, we're going to have to use false color mapping. Okay, we're going to have to take the cooler blues and we're going to have to make them very blue, and then the hotter blues we're going to have to make them, map that over to red so that we can see the temperature differences inside this star forming region, and then eventually it's going to collapse into this dark opaque area, historical opaque area, which is very hard to see into. And if we want to, we're going to have to use wavelengths that can see around all these dust particles. We're going to be looking at that in the infrared. And what we see in the infrared is that as all of this stuff collapses, just that tiny average random bit of angular momentum that might occur in there, it's going to concentrate. It's going to concentrate. It causes this little piece of this star forming region to the stellar nebula to begin spinning this way, and this one's going to spin this way, and this one's going to spin this way. It's all very random. Okay, and they're going to collapse. And again, we have heating, except now it's beginning to get dense enough that the particles are rubbing against each other, and that's going to create more thermal energy. Okay, and these things are going to begin to heat up very, very rapidly. Um, very, very rapidly. And if they weren't blocked by this stellar region, the dust in this stellar region, they would glow very, very brightly. Okay, but as they heat up, they're able to radiate a lot more energy. Now, I'm not sure if we ran across this, but the energy radiation goes as the fourth power of the temperature. So this climbs to a few dozen Kelvin above absolute zero to millions of degrees above absolute zero. It's going to radiate very, very quickly. So this process starts to happen a lot more quickly. So these things are spinning, and there's little eddies inside there where stuff is accumulating inside the disk of this protostar, and things are collapsing into the center of this protostar. Okay, and then things are going to collide. Things where you're going to lose a little bit of momentum, or angular momentum. It's going to slide toward the center, and things that are going to gain a little bit of angular momentum, and they're going to move outward toward the outer portion of the thing, and they're going to create little things, little whirlpools, and these little whirlpools are going to form protoplanets and protostars right there in the center. And what's happening in that protostar? What's happening in that protostar is things are beginning to heat up. The compression and the gravity and the mass are causing everything to heat up. And if we're very lucky, what's going to happen at the very center of that, it's going to reach the pressure and the temperature and the density, all three are required, pressure, temperature, density, that we're going to begin to slam hydrogen atoms together, and we're going to fuse them into helium. And that's the beginning of stellar ignition. At the stellar ignition, that's my lady friend right there. Okay. The stellar ignition is going to begin to, it's going to begin to give off light, and then suddenly there's this light pressure. The light, remember, it was the light pressure of the infrared images, the infrared photons that was holding up that molecular gas cloud. Well, that's happening again in this much smaller, much more intense form. There's light pressure from the fusion itself. These are gamma rays, and they're ricocheting off everything all over the place, and they're being split into two photons that are now, these aren't just gamma rays, they're now X rays, and then they're making their way all the way down to the visible light and the infrared, and all of these photons are bouncing around all over the place, and they're providing a pressure, a light pressure that's holding this star up. And that's the stability. That's what we call the hydrostatic balance. In a living star, in a main sequence star, the light pressure is holding it up against the gravitational pressure. And that can be stable for billions of years. In our case of our own star, that will be stable for about 10 billion years total. In smaller stars, it lasts a lot longer. In the huge O-type stars, it's only going to last a million or so years. It's going to burn through all of that fuel. And when the fuel goes away, so does the light pressure, and it begins to collapse again. Now let's talk about different stars. How do we get O-types? How do we get G stars like our own? You get little tiny red ones that don't last forever. Well, what's happening there is that we have these collections of stars, these protostars. Okay, some places you're going to collect so much mass. So much mass. You're going to have a lot of angular momentum. It's going to spin around very, very quickly. And you're going to collect so much angular momentum, it's going to spin itself apart. And you're not, so there's an upper limit to the masses of the stars. It's about 80 solar masses. We think that in the very early universe, the hydrogen and the helium was so pure, absent any contaminants like oxygen and all of the other things that are produced in late main sequence stars, that we could have had stars that were up to 160 solar masses. Okay, but currently in our current epoch, 80 solar masses seems to be the upper limit. Now, down at the bottom end, we can create, and just imagine, just like when you break apart, it's like you take a little mud ball, some dried mud ball, and you break it apart. You get a few chunks, and you get a lot of smaller stuff. Okay, and so we're going to get a lot smaller stellar bodies as well. You're going to get many more. Please. Thank you. We're going to get many more G-type stars than we're going to get O-type stars. And then of the G-type stars, we're going to get fewer of those than we are going to get your lower red dwarfs, the M and the Ks. Now, what's the lower limit? We talked about the upper limit. Let's talk about the lower limit. Remember, I talked about how those solar masses are compressing each other, and we're getting down to the point where we can actually we can actually have the conditions necessary for fusion, hydrogen fusion, which is going to power a main sequence star. Okay, at the very low end, we have failed stars, we have brown dwarfs, we have these balls of gas that form, but they don't reach the point where fusion can occur, and these are called brown dwarfs, failed stars. Some of them, we think that there are many of these floating between the visible stars, the visible main sequence stars. I'm sorry, let me pause this for a moment.